Ben, thank you again. Appreciate that introduction. And I will let Dave Roush and Jeff start the presentation and introduce themselves. So go ahead, Dave. Go ahead and get started. Thanks.
Thanks, Brian. Thanks, Ben. Again, appreciate the time and the opportunity here. My name is Dave Roush. I'm a business development manager for Phoenix Controls. I work a lot, obviously, with critical environments, both in the healthcare range and the research range. Been doing this for about 14 years, and I have a lot of experience with technical committees and codes for the ASHRAE. And the most important thing for you guys, for us to provide to you guys is obviously just some of the background and things like that we can help and work together on and do for you. And we'll start with that, like Benjamin said. We do have this as an AIA accredited course, so do reach out if you need that PDH. I know it's getting close to the end of the year. Many of you might be a little behind in your PDH credits. We can certainly help that. And I also want to put a plug in. If there's something that we don't get into detail on today, but you want to know more about, we have a significant library being built with AIA. If you need more, just let us know and we can get you some more credits. All right. And Jeff, go ahead. You can introduce yourself now.
Thanks a lot. I appreciate that. And thanks everybody for joining. My name is Jeff Mumford. I'm a partner at LabWorks International. I've been in this industry for about 25 years now, doing all different types of critical environments. My background is I am a mechanical engineer. I've designed, installed, and been involved in all kinds of different critical environment life sciences applications. And today we're going to talk a little bit about some of the experiences we've had predominantly around clean rooms and factors that impact how to get clean rooms to perform effectively.
All right, well, very good. Thank you, Jeff. I'll go ahead and start, and then I'll hand it off to Jeff for the once we get past the clean room codes and stuff. So for like we said, we're going to talk about a number of different things today. We're going to talk about clean rooms and clean room codes. And I know many of you guys out there may be familiar with Venturis and Phoenix Controls, and I'm just going to do a quick, outline of who we are, what we do, why we do what we do, because I think that'll kind of help understand the connection between what we do for critical environments and clean rooms. And then we're going to provide some clean room construction guidelines or just what to look for and some good case studies, and that's where Jeff comes in. He's got obviously some great experience with that, and he's learned a lot, and obviously if we can share that with you guys and work together, that'll be great. And then Benjamin has asked for some time at the end here to do some regional updates, so we'll give him time for that. So we've got about an hour in which we're going to talk, and then we'll leave it open for some questions and see if we can't help you out. So real quick, Phoenix Controls, who we are. Basically, what we do, we started about since 1986. We started out in fume hood controls, and we developed this technology called a Venturi valve that allowed us to be able to provide good room pressurization and maintain good environmental controls for areas that need pressurization, for areas that need safety and containment, right? And we've certainly evolved over the years and developed products and solutions that support that, along with a lot of data aggregation, right? And data analysis, because obviously these facilities not only have to maintain certain compliances, which we're going to learn about later on in the conversation, but we got to be able to have that data to make sure that they're performing well and we can maintain them, right? So we've evolved from not only maintaining and regulating the airflow, but we can now present it in a way that helps the facility maintain their quality and their compliance, right? And we have a significant amount of startup and engineered solution support. We have reps from all over the country, from East Coast to West Coast, and we've got a good group down there in the Southeast to support you guys there with Ben. But we're also global, right? And we take that responsibility very close to heart, because everything we do has a safety or compliance mechanism to it, and it either costs a lot of money or it can cost, obviously, in deaths as well. So we want to be able to make sure that we maintain the quality that we say we're going to. And so we have a strategic rep partnership that comes through a lot of training through factory, to support guys like you, to keep that responsibility up, right? And Phoenix Controls focuses strictly on critical environments, right? And we do that through strategic partnerships, not only from a construction perspective, but also from an end user and consultant perspective. We've learned a ton especially in the last 10 to 15 years, in maintaining environmental quality and maintaining good compliance measures. Jeff, you want to go ahead and talk through this one?
Sure, that's great. Thanks, David. So quick introduction to LabWorks International for those that we haven't come across before. Our business is controlled environments, be it clean rooms, temperature test chambers, stability chambers, low temperature, pharmaceutical grade, vaccine freezers, and everything in between. Our markets are the life sciences industry, so we predominantly play with pharmaceutical companies, higher ed research companies, investigative science companies, and healthcare units, and sometimes a mix of all three. Some of our customers you're familiar with. We've done a couple big clean rooms for Mayo Clinic, for Sanofi Pasteur, Merck, GSK, and a pile of others right across North America. We do work in anywhere in the United States and Canada, and in a few select other markets, depending on where the job is. And we're based out of Toronto, Canada. So I'm going to spend a few minutes, and I'm going to talk about clean room systems specifically. So I won't be talking about freezers, vaccines, incubators, the rest of it. That being said, if there are any questions on any of the rest of it when we're finished, always feel free to reach out to me, and we'd be happy to talk about it. But I'm going to talk about our experience in life science grade clean room systems, and it actually sounds pretty relevant because we've done quite a number of units that are in cell and gene therapy type installations. And with those, we've learned a lot of good lessons that can help. And I've really geared this presentation to be about building the units and things to look out for, because I think that suits the audience in this case. Next slide, David. So a quick refresher for those who aren't as familiar on the design side of controlled environment clean rooms. There's a few standards that really govern a lot of how these are put together. The predominant one is ISO 14644, clean rooms and associated environments. That ISO standard is maintained by an organization called IEST, which is the Institute of Environmental Sciences and Technology, and they have developed and maintained that document, and it really is, I'd say the Bible for building clean rooms. Within that, and then when you move to life sciences, you run into GMP and CGMP, good manufacturing practice, which has another layer of requirements that go on top of the ISO requirements. And as we get into the mechanical side of it, and where we interface with Phoenix quite regularly, is on the HVAC side of clean rooms. And ASHRAE has a great design guide out for the fundamental systems and performance of clean rooms, and it gives a lot of practical design guidance. And then for those who are involved in medicinal products, either in healthcare facilities or in compounding facilities by third-party companies like Baxter, for example, there's the United States Pharmacopoeia, or USP, has a couple chapters, 797 and 800, that relate to clean rooms in compounding facilities. And we'll have a few examples of those to talk through as well. Next slide, Dave. So within ISO 14644, there are four, well, there's more than four chapters, but there's four that really relate to the things that we do. And there's one in particular that impacts building of the clean room as opposed to operation of the clean room. So, number one is the classification for air cleanliness, and that's typically decided by the people who are using the clean room and have to come up with the level of cleanliness they need for the operation that they're providing. The second is how they are going to plan to test and monitor that clean room over the course of its operation to make sure that it stays in compliance. And you can get situations where people actively monitor through particulate monitoring systems, or they come in every 6 months and they do a retest of their facility. So you kind of get a combination of the two methods. The third section is metrology and test methods. So that's really coming in and what is your procedure and protocol to ensure that you're in compliance with the ISO standard that you're looking for. And then Section 4 is the one that really impacts, and the one I'm going to talk mostly about today, is the design, construction, and startup of clean room facilities, and what makes them important. So as we look at get into life sciences clean rooms, the photo you see on the right there is a large regenerative medicine facility that we built recently, and I'm going to talk mostly about this type of facility. So the first most important aspect of it is contamination control to the ISO standard that is built. So you'll hear things like ISO 6, ISO 5, ISO 7, 8, 9, 9 being the least stringent, ISO 1 being the most stringent. Most facilities themselves fall into the 5 to 8 range, depending on what procedure is being done in them. Second most important part of it is pressurization control. So to maintain that cleanliness standard, you're trying to pressurize from most clean to least clean, but then there are some exceptions when you get into hazardous applications or biosafety level type applications, and we'll talk about that. The third criteria is temperature control. Sometimes it's related to the process. The process needs a very specific temperature in terms of what's happening in the space, and otherwise temperature to suit the occupants of the room. In many of these cases, the people who are going in during operation have 2 or 3 levels of clean room garb on top of themselves, and in doing that, it gets very warm. So usually these spaces are kept quite a bit cooler than normal, in the 65 to 68 Fahrenheit range, and it needs to be considered in the design phase. One of the biggest issues we've seen on projects is material compatibility. If you're in a life sciences application, typically it's categorized as aseptic or sterile. And when you have an aseptic application, you have to go through a regular disinfection and sterilization of the space. And what that means is that they're typically taking a chemical like Spore Cleanse or Decon Quat or some other very aggressive germicide, something that's going to kill living organisms. And they wipe down every surface in the room on a daily basis. And then they follow it up with a sterilization protocol, which is normally isopropyl alcohol. And so you've got this double wipe down where you're taking an aggressive material and you're wiping every surface, and then you're sterilizing it afterwards. And in doing that, those chemicals are destructive to most materials. So standard paints, standard aluminum, standard paints or plastic surfaces, things like that will not stand up to it. And over a short period of time, they'll become colored, discolored, start to degrade. If you've got 304 stainless, it'll rust. You'll get into situations like that. So material compatibility becomes a very important part of the whole job when you're making sure that everything is going to work properly together. We work with Phoenix a lot in making sure that process air management happens the way it's supposed to, from an exhaust, a makeup, and a recirculation standpoint. And then if you're into the pharmaceutical side of things, monitoring and reporting becomes very important. And there's a chapter 21 CFR Part 11 that gets into how all of the monitoring and data acquisition needs to happen. And that needs to be planned and ensured it happens in advance because it's tough to do afterwards. Next slide. So key factors in the design that things that we've learned over time and experience, a constant supply air flow rate needs to be maintained for the facility to operate properly. So, in an ISO 7 facility, or you may have heard in the old Fed standards, a class 10,000 facility, you would typically run something in the neighborhood of 60 air changes an hour up to possibly 100 air changes an hour. And you don't want that value fluctuating. It needs to stay at that rate to meet the cleanliness standards and the certification standards you have. So what that means is that on the design side of things, you need to vary sometimes your exhaust or your return rate to maintain the pressures that you're looking for. So you've got a standard constant supply to the space, temperature controlled, and now you might have some biosafety cabinets in the space where you're exhausting air, and then you'll use your return air to maintain pressure differential. And in doing that, our experience is you need a high quality Venturi valve, and we pick Phoenix all the time. and you offset flows to ensure that you maintain that pressure differential. Otherwise, you can get in a situation where your rooms won't pass certification because somebody opens the door in one location and all of a sudden your room goes negative for a moment, and dirtier air than is allowed gets into the space and you won't pass your test. And when you get into the higher level ISO classes like 5 and 6, it's very easy not to pass a test if your pressure control is not correct. Next slide. So this is just a representation, and I'm going to show you two different types of, and for very important purposes. So the room on the left is a clean room suite where you would enter in a gowning room, and you see the +1, so that means it's +1 positive pressure to the adjacent surrounding areas. In that area, you would get out of your dirty gear. It would typically be an ISO 8 type environment. You put on your clean room gear, and then you would enter the prep room. The prep room is double positive. So now you're something like 20 pascals positive to the surrounding environment. So you're positive to the gowning room as well. And in that area, it would be a clean area, typically ISO 8 or ISO 7. And you would get all of your material ready to do whatever function it is that you were doing in the actual clean space. The next step would be moving into the clean room itself, which was shown as triple positive. That might be something like an ISO 5 or ISO 6 space, where they're actually doing some production or some work in there. Typically, these higher end clean room areas are kept as small a footprint as possible because they run very high air changes. An ISO 5 clean room might run 240 air changes an hour. You know, if you contrast that to a typical office space that might run at 2 or 3 air changes an hour, you get a concept of how much air is traveling through that space. And that clean room then is at triple positive. So in other words, you see the cascade of air from the clean room leaks through the doors to the prep room, into the gowning room, and then out to the adjacent space. To maintain a pressure differential, you always have to have a small amount of leakage, and that might be something as small as 25 or 50 CFM that typically leaks through the doors to the adjacent space from cleanest to the next clean to dirtiest. And by controlling that, you're able to maintain the proper cascade of everything. Where it gets more complicated on the right side is another example, and this would be something like a vector production suite for regenerative medicine, where they're taking viruses and genetically manipulating them to do treatments. In these cases, that clean room needs to be negative to the prep room so that you don't have air escaping the clean room because there's always that risk of contamination due to the fact you're dealing with viral vectors. So in these cases, you can see where we need to change the pressure model from positive in the gowning room to triple positive in the prep room, single positive in the clean room, and then the air flows from the prep room into both the clean room and the gowning room. So there's no opportunity for both dirty air from the unconditioned areas to get into the cleanest area, nor is there an opportunity for air to escape the clean room. But the thing that really becomes different is, in this example, the one on the right, the prep room has to be at the same cleanliness class as the clean room. So if the clean room is ISO 5, the prep room needs to be ISO 5 because you can't have dirtier air entering the cleaner space. So they both have to be equally clean. Next slide, David. So very quick summary just in terms of what we're talking about when we talk about ISO classes, or if you're familiar with the Federal Standard 209, you can see what the grades are. For those that are working in the pharmaceutical side or regenerative medicine, you'll start hearing things like grade B, grade C, grade D. So a grade B would be equivalent to an ISO 5 at rest or an ISO 7 in operation. A grade C would be an ISO 7 and a grade D would be an ISO 8. So you'll run across these different categorizations, and they really relate to both pressures and to air changes an hour that result, based on these design guides, you can achieve a certain level of particulate counts in the space. And ultimately, to pass the test, you have to have the particles within the acceptable range, depending on your ISO class. Next slide.
All right, thank you, Jeff. So obviously this is an area where we felt it was appropriate to kind of get into why is it that the Venturi valve is typically used for these applications versus a VAB box. right? And I think this is helpful for a lot of you guys who aren't familiar with the Venturi, how it works, and why we're able to maintain the pressure and the air change rates in a stable manner, like Jeff was talking about earlier. Because obviously for these type of applications, it's downtime and it's in spread of infectious viruses and things. So the difference between a VAB box and a Venturi is quite significant. Now you can see from the bottom left-hand corner a picture of a VAB box. I know all you guys know, what a VAB box is and how it finds its position, right? It uses that damper inside there, and it's based on a signal or feedback, but it's based on the sensing of the pressure in the ductwork, right? And so you have a lot of pressure fluctuations going on in the ductwork, and you have a lot of pressure fluctuations going on when you're entering and leaving the room, just based on occupancy activity. And so what happens is with those sensors on the damper is basically that damper is constantly trying to find its position, right? So it senses a difference in pressure, so it'll overshoot, undershoot, overshoot, undershoot, so on and so forth, and you get these pressure fluctuations, these large swings. And I'll show you what that looks like from a graph standpoint here in just a minute, given the sensor technology that we've seen as of late. But basically, now that you understand where the guidelines and the requirements are for these spaces, you can understand why that provides a risk, right? So if you have these pressure fluctuations, that's going to be really hard to be able to stabilize that airflow and maintain that direction that's needed, for these type of spaces. Now, the Venturi valve, like I said, back in 1986 when we developed this technology, and it certainly has evolved since then. But what we did is, because we knew of this phenomenon, is we created this Venturi that has this cone and funnel assembly inside it with a spring. And that spring basically negates or neutralizes any of those pressure fluctuations that occur just based on activity, basic temperature control and things of that nature. So as you have airflow coming through that, and if the pressure goes up or down based on activity, that spring inside there will neutralize it, right? Now, the other part of it that's very different from the VAB box is that position equals flow for us. So as soon as you want to go to a certain flow, it goes to a position, because these valves have been characterized at the factory, so we know exactly what position equals what flow within a plus or minus 5%. And we can do that on any part of that flow range. So we can do that at low flows, lower pressures, high flows, higher pressures. And so you can see on that flow curve at the bottom right corner, that red line, that allows us to have a lot of stability, a lot of flexibility for turn down, very accurate at the lower side and even at the higher side. And so we use every point on that curve to characterize the valve, so we can get within plus or minus 5% at any point. So again, good, accurate, repeatable, stable directional flow, which is needed for these applications, is what this Venturi has been designed to do, right? Not the VAB box. And so I'll share with you what this graph looks like. Now, this was, like I said, I talked a little bit about partnerships that we've created and had for critical environments, specifically to critical environments. And this is coming from a hospital where we have high air change rates that we're looking at ORs, and we need to be able to maintain a positive pressure in those in order to keep that space sterile, keep that space clean. And you can see from the sensing technology out there that's used to monitor the environment and help understand the environmental quality, you can see the fluctuations from a VAB box. Now, for this particular consultant, when he's looking at this from a reliability standpoint back to infection control management, he's looking at a standard deviation of needing around 0.01 in order for the data to be returned in a good health way to understand what the infectious risk is. So this graph is basically showing those pressure fluctuations, and this is a constant volume ducted return OR, where you have a VAB box spiking all, from 7 a.m. to 3 p.m. You can see where the standard deviations are going. The green line that you see on there is basically from the Venturi valve. That Phoenix Venturi valve is able to maintain that good, stable directional flow, which again reduces the risk of any kind of pressure sways within those spaces. We even did a study to show in an ICU space where we did some comparisons how much more effectively a Venturi valve can move those particulates out of a space to help from an infection control perspective. So even from an efficiency standpoint, when you're looking at higher air change rates, you do see that you get a more effective removal, and that's what the ISO standard's about. But even at the lower air change rates, when you're trying to take on occupancy times, like if it's unoccupied, you can reduce those air change rates. You can maintain some sustainable levels, with your equipment. Again, you're getting a much more effective purge and movement of those particulates out of that space, keeping that space clean even at the lower air change rates. And again, that all goes back to the phenomena of the VAB box trying to find its position, where the Venturi doesn't have to do that. We go straight to position. We maintain that stable directional flow. We're getting a more effective air exchange in that space, and we're able to keep those spaces cleaner, right, and more reliable. And again, just to show that, when and I think Jeff will talk a little bit about this, when, a lot of times what facilities will do is they will increase their air change rates in order to try and maintain, a reliability, if you will, on directional flow. And there was a study that was done in the American Journal of Infection Control to show that for every 2 air changes that you increase your space, you're costing that, depending on your thermal zone or your climate zone, you are costing that space about $2,000 per year per space, right? So for every 2 air changes that you increase in order to maintain that directional flow or that quality of that space. And so that can be pretty cost effective. Obviously for clean rooms, if you got to go higher on the air change rates in order to maintain, that's what you're going to do. Again, that's going to cost you from an energy perspective. Sometimes facilities don't care because they can't afford the downtime and the non-compliance, right? But here you can manage things together, not only with the air change rates per code, you can maintain the pressure, you can maintain the compliance in a lot more efficient manner. Jeff, back to you.
Great. Thanks, David. So I'm going to talk a bit more now about some real specific construction details that we've run into. I'm going to use a couple of example jobs to go through that. And then after that, we're going to actually get in some case study work where LabWorks and Phoenix have worked together, and the approach to how we tackle these. The next slide. So our sample facility, this is an actual project. It's actually the one you saw the photo of at the start of our presentation. It's a cell manufacturing and viral vector facility. So 20,000 square feet of GMP space, 10,000 of which was dedicated to clean rooms. We ran 8 grade B cell therapy suites and 2 grade B suites that were dedicated to viral vectors, so taking viruses and genetically remanipulating them for other purposes, and then a quality control lab. So good example, and the perfect reason why precise pressure control in a clean room application becomes really important, as well as the quality and how you build the facility. Next step. All right, so this is a Revit model we had done when we were building the suite. You can see the amount of material that is put into these facilities. Obviously, clean rooms are expensive, both from a square footage standpoint and standpoint, so they do tend to put a large amount of material into the space that needs to be very carefully coordinated. Typical to a lot of these, you see you'll have a clean corridor area, well, an entry area, gowning into a clean corridor, into a production suite, exiting to a dirty corridor, and then out of the facility, and that's how this facility was built. It was actually into a research building up on the 12th floor, with a glass curtain wall type construction, which added some complications to it, because even with the best curtain walls, as I'm sure you guys know more than us, when you have high winds, you can get pressure differentials in the space between the windward and leeward side of the building. And that's where, it was very important to have really precise pressure control for the suite, the clean room suite portion of it, to make sure none of those other factors impacted how the room operated. Next slide. So this is the approach we take typically to it. Using Phoenix air valves, we're able to have you see on the left side an APM, or air pressure monitoring system. So we're actually tracking and monitoring and recording that the room is performing as it's supposed to. In the gowning room, which would be your 10207A facility here, we have a supply and exhaust duct, and we're tracking the air differential to maintain the pressure that we want. And then as we get into the production suite side of it, 10207, now we have a couple of exhausted biosafety cabinets that have flow tracking Venturis on them, as well, and then a general exhaust, which is used to compensate for if one of the biosafety cabinets happens to be shut down for any reason. And then we have a general supply side. So all of these components are integrated together. They operate in tandem to ensure that the pressure is controlled precisely so that our clean space is positive to our gowning space, which is positive to the general space that we're operating in. And that cascade becomes really important to maintain the cleanliness levels that we needed in a grade B, which is ISO 5 at rest. So basically, if you saw this from the inside, a lot of your ceiling is almost all HEPA filtered. Next slide. So as we talk about how we build these, site preparation is really important. If you have an opportunity to read the ISO 14644-4 document, they've got a couple of appendices that talk about site preparation and about having a protocol for constructing the clean rooms. And the reason for that is you want to be building these in the cleanest environment that you can, that's practical, so that you're limiting the amount of future cleaning and then potential contaminants that could end up in the space. So even from the initial rough-ins that we do ahead of time, we work with partners on the HVAC side and/or deploy some of it ourselves. And you can see all of the ductwork is protected. The space is kept very clean. All material is removed when it's not in use, and we try to limit the amount of material that is used for construction in the space of the clean room, simply to ensure that it's kept as clean as possible. So generally, we request and we have a staging area outside of the clean room area. That's where cutting is done, or any kind of the dirty process involved with putting the material together. Even we use a modular clean room approach, so we're using modular panels, largely pre-assembled or preset for assembly, but there's always some form of cutting that would need to be required as you get into it. So generally, all the prep work's done ahead of time before you start it, and then you get into, what is your protocol for doing? It's okay, David. You get in your protocol of what are you doing to build the clean room itself. We sit down ourselves and go through with each of the contractors that are involved in the clean room, and we have a three-level LabWorks has a three-level protocol program where we basically have our pre-installation protocol, our installation protocol, and then our finishing protocol. And in doing that, all of the trades are very familiar with making sure that the space is kept as clean as possible. All of the finishes are protected. You can see the photo there is from a new job we did at Mayo Clinic, their Discovery Square facility, and everything was kept out of the clean room portion itself. It was all protected ahead of time, and we had posted everywhere the requirements for working in the clean room space so that everyone was well aware of it. And that is also a requirement in ISO 14644. You'll find that discussion around how that protocol should work. A common issue that we have on this, like all other ones, is just simply, some trades, especially those that haven't worked in that type of environment before, don't appreciate the level of care that needs to happen, and you have to take that out of their habits. Next slide. Many modular systems, ours included, start with a ceiling installation. So, again, you're trying to keep a very clean facility where you have a minimal amount of interferences and a minimal amount of accumulation of material that could cause contamination in the future. So we coordinate the objective is to coordinate all your services well ahead of time before you start your clean room. You don't want to be going in and realizing, we forgot to run a bunch of gas lines and have to try to work in and around the clean room system once it's starting to be assembled. Some of the really good lessons we learned, and common ones, is it sounds obvious, and I'm sure you're aware of it, but generally in these buildings the floor is not flat. You're putting up a concrete structure. It might be pre-stressed. It doesn't settle out. There's a tolerance in how it settles out. And we've seen cases where, you've got situations where the slab might be varying 1 inch to 1.5 inches over 10,000 square feet, which doesn't sound like a big deal, except that the ceiling is perfectly flat. So one of the really important things we learned early on these jobs is that everyone needs to work from the same baseline. And when I say everyone, your person who's installing the ductwork or the piping or electrical services has to have the same starting point as the clean room supplier, because otherwise what we think is 10 feet off the ground might be 9 feet 11.5 inches to the ductwork guy, because they took their baseline point from a different location, and now you end up with a situation where you can have a lot of conflicts. So one of the very first things we do is make sure that we go back and work with everyone to get a common point to start all of our measurements from, and we work from there. Working through, we're big fans of Revit, doing coordination and clash detection, using Navisworks and other tools like that help a lot. Clean rooms are extremely congested areas from a services standpoint. So the more coordination that can be done ahead of time, the better your job will flow in the future. It doesn't get rid of everything, but it does really help when there's some good coordination in advance. And then our other common issue is just to limit the access to the clean room area. So typically we've got some form of protective hoarding and locked up area, so that you don't get people walking through the area, using it as a pathway to other areas, and or inadvertently becoming a storage area when some people are just looking for somewhere to dump stuff. Next slide. So next step in a lot of installations is getting the wall construction in place. This whole process of the ceilings and the walls become critically important for the performance of the room. If you're going to pass the higher level clean room standards, the rooms need to be sealed perfectly. And then, when I say they leak through the doors, that the idea is that you control the leakage, exactly how much air is leaking from it, so that the pressure control system can provide just the right amount of air and not too much air, as David mentioned. The way of solving a poorly constructed room is you have to provide a whole bunch more air than you should, which causes all other kinds of problems as you get into commissioning and operation. So proper attention to detail and making sure that everything is sealed properly is really critically important. We do a lot of work in terms of modeling the locations of everything. You'll see the wall construction there with a bunch of tape and locations for cutouts. There's false service ways built into it so that everything is planned ahead of time. Some of our real common issues that we've run into is, do you install flooring through the facility first, or do you put the walls in and then, seal to the walls with the flooring? My own preference is I think you get a much better finish when the walls go in and you're coving to the wall, rather than sticking the walls on top of like an epoxy or resilient floor and then trying to add coving to it. The flatness of the building floor, I brought that up before. We run into that both from how the walls work, because they are, they're modular, they're perfectly cut, and then also in the doors, to make sure that you actually get the expected performance out of the doors. If the floor, basically rises as the door opens, you have to raise the door and you get larger openings underneath, and you have drop-down sweeps, and then basically you start impacting the way that your room performs. So you really want to try to make sure you get the best floor flatness level that you can get in that particular area. In most cases, we get into installing leveling compound to try to get something like an FF50 if we can, or an FL35 type performance in the space. Coordinations of services is a big deal. Making sure that everything is where you need it, and that you've got it all planned out as we go through it. One of the common things we run into is the idea that, we build these suites which are full of equipment, but some of the equipment can't go through the doors. So we do a lot of planning around knockout walls to ensure that you can get the equipment into space, or you can remove it in the future if you're going to upgrade it or service it. But again, at the same time, it's really important that those knockout walls be perfectly sealed, and that you've got a really good pressure management control system in place, so that you're not going to impact things as it runs. And then one of the big last common issues, and you saw in some of my previous photos, is wall damage. We ship tons and tons of wall protection with every job that we do, simply because it's, these clean room panels are sensitive to damage. You don't want people running around with metal-edged carts and, leaning things up against it where, conduit or something can hit it, strike it, and all of a sudden you've damaged the surface. Because the panels are made to be cleaned with really aggressive chemicals, it's very important that we keep the surface continuity, perfect when it's built. Next slide. I did mention that there's piles of different doors that you're going to see in clean rooms. Typical to any kind of clean room door system is they have to be interlocked. Sometimes that's through mag locks and hard security like card access systems. Other times we've just used a light indicator system, so green is good, red is bad, and you proceed once you've got a green light to do so. The doors are important because not that they're to seal perfectly, but they're to seal the correct amount. So the top left picture, you see a swing door. That door was designed to leak approximately 25 CFM with the pressure differential that we wanted to achieve. If that door did not seal properly, we would have to increase the amount of supply air until such point as we were able to get to the pressure differential that we wanted. And you can understand where that becomes an issue, in that there's only so much flexibility in the HVAC systems to add more and more air if your room leaks. Where it gets even more complicated is when you're doing a biosafety or a viral vector lab or a hazardous compounding room, USP 797 or 800, because now you've got a clean room that's negative to potentially the surrounding space. And in doing that, if your room leaks, you're bringing in dirty air into your room. So it's really important that your air only comes through the door and only from an area that's clean enough. So there are common issues that we run into on the door systems. And I keep going back to the flatness of the floor, but it's a common issue. If you don't get a good flatness level, the space under the door needs to increase so that the door can open properly. And in doing that, your drop-down sweeps sometimes don't seal as well as you'd want them to. So the better the floor finish you can get, the better the performance out of the clean room you're going to achieve. The other one big issue we have is trade access during construction. Once the doors are in place, they're built to be interlocked. As soon as you power them up, you're going to restrict access. So you're trying to really, in your construction protocol, in ours, for example, we try to get a lot of the trades out of the space before we move to stage 3 of the protocol, because at that point we're basically locking it down. Everyone needs to be wearing clean room garb when they go in to do the finishing work, and you don't want a situation where you're handing out tons and tons of access cards to try to get people to actually be able to do work in the space. Next slide. Other big issues to consider, embedded services and casework. You see on the right side, you've got gas services, hazardous monitoring, electrical outlets. So all of these need to be planned well in advance. Every penetration into the clean room needs to be very, very carefully sealed, because you've got two situations. If you're in a negative pressure environment, you're going to be leaking dirty air into your clean room. It's a BSL type clean room. And if it's a positive pressurized clean room, well, now you're just giving it other pathways for the air to escape, and then you're having to create a bigger pressure or flow differential to achieve the pressure differential that you're looking for. So a lot of attention needs to be had around sealing these services. The ones you see are sealed where they penetrate into the space, but they're also sealed at the top of the clean room assembly where they're fed from. And we make sure that they're completely sealed in both cases, because things like electrical outlets can leak 15 to 20 CFM each if you have them wide open and you don't seal the conduits. So you want to make sure that you've got a fairly tight seal all the way around for those outlets. Some of our real common issues that we run into when it gets into doing the services and casework in these facilities is, number one, scope of supply. A lot of the casework needs to be designed to accommodate the clean room material. So clean room corners are coved, the flooring is coved, We've seen where people have brought in casework after a job is done, and then they can't place it against the wall because the legs are not offset in as needs to be with a clean room, so that it can't accommodate for the floor coving that's in place, or the wall coving for that matter. The other big one is the selection of materials to match the cleaning protocol. The clean room vendors are really good. Generally, your casework guys will be really good. They'll understand all of that. Where you run into some problems are guys like your fire alarm vendors. When the owner wants to install a wireless access point system, like for Wi-Fi, things like that, the material that's being placed in there needs to be able to stand up to the cleaning chemicals that are used. And we've seen cases where, exit signs or smoke detectors, quite honestly, just start to deteriorate because they can't handle the cleaning chemical. So there needs to be that coordination to make sure that all trades are providing suitable material to be used in there, and usually you'll want to see them checked against a material compatibility chart. There's a few of those available out there that you can verify the material will match the cleaning protocol that the owner has established. Next slide. So I'm going to get into a few different examples of jobs, a few where we've worked with Phoenix reps and a couple where we didn't, and some of the lessons that we've learned in doing these and where it becomes important. So the first one is, this is a really big cancer treatment hospital, Princess Margaret Cancer Center. We did their USP compounding clean room. It involved both non-hazardous compounding, which is sterile compounding, so your positive pressure to the surrounding environment, and then sterile hazardous compounding, which is typically cancer treatments for cytotoxic drugs, and in those cases, those rooms need to be kept negative pressure to the surrounding environments. On top of it, we have a hazardous storage area for the cytotoxic drug product, and then in the photo on top, you see their staging area, and that's where all the product that's been compounded then is packaged and put in place for distribution throughout the rest of the healthcare enterprise. And to give you an idea, this was like a 1,200 square foot facility, and our project to do that was about 1.4 million to deliver that scope of work. Next slide. So this represents kind of from a pressure control and how LabWorks and Phoenix work together to accomplish the pressure requirements of this clean space. I didn't mention it, but in this case, we were a Division 13 specialty contractor. Our contract included the clean room and everything associated with the clean room. So everything you saw in those pictures we supplied, and we supplied the HVAC system that met the requirements of the space. So in doing that, we deployed 26 air valves, 5 pressure monitoring zones, and you can see those down in the bottom, the different pressure monitors in the little red squares, and how they were used throughout the space. We were responsible for temperature control, and then we had exhaust valves on the biosafety cabinets to help ensure all of the pressure requirements were met. So one of the issues we encountered on this one that had to be planned or dealt with afterwards was, there is a certain amount of air pressure that's required for these systems to operate properly. On the supply side, you're going through an air valve that could use anywhere from 0.3 inches of static up to 1 inch of static, and then from there you're going into a HEPA filter unit, which would like up to another inch of static to make sure that you're able to compensate as the filter loads up. So your supply systems have to have enough capacity to meet the static loads that you're running into. It's obviously more of a design side thing, but as you get into commissioning and balancing and everything else, it becomes pretty important. On this job, the engineer didn't allow for enough on the exhaust side, and so they had to go back and actually increase the size of the fan motors just so that they could get the static up to where it needed to be for those biosafety cabinets. So, obviously more on the design side, but also when you get into the commissioning side, it becomes very important, because if your room was leaking and you didn't have really good precision control, trying to get that extra CFM or that extra static would become an even bigger problem. Next slide. This is another hospital project, Centenary. Again, an example, for those who've done these before, you'll know that USP back in 2016 put out a new document that required all sterile compounding to be moved into clean room facilities. So hospitals across the U.S. and Canada have been busy upgrading all of their compounding facilities. But they're great examples for clean rooms in general, be it cellular research or regenerative medicine, et cetera. So in this case, this was a sterile non-hazardous compounding with a sterile hazardous compounding again, anteroom, staging area. Again, roughly 1,000 square feet, and had a few other unique opportunities for us to work with Phoenix and to meet the requirements of the project. David, next slide. So in this case, we deployed a system using the Venturi valves. We had 3 pressure zones. So we had the preparation area or the anterooms. We had the hazardous area, and then we had the non-hazardous area. We used the system to maintain the pressures, but also monitor the air change rates. So we were meeting the air change requirement to do temperature control. And we used fan-powered HEPA units or fan filter units in the space to lessen the amount of static impact on the base building services. And we were able to network all of those through the control system as well with reheat. And so what that allowed us to do is take a nice clean bundle, control everything very, very precisely, meet the clean room requirements, report it back. In this case, it was a Honeywell EBI system that was monitoring everything, and back to the Honeywell system. And so you've got all of the reporting and management that you need, and we were able to do a really nice precise control. And using the fan filter units in this case, we were able to offset some of the pressure issues that could have happened by providing an extra bit of pull on the fan units as we were designing it. Next slide. So here's an example. This was one, it was not completely turnkey. We did this for Mayo Clinic about 1.5 years ago. It's their advanced manufacturing center for regenerative products. In this case, we were responsible for the modular rooms, the casework, the doors, flooring, basically everything except the HVAC. It was 4,500 square feet of grade B and grade C processing suites, 5 independent rooms where they're doing different types of gene therapy. In this case, we worked with HOK and Mortensen. And a fairly decent sized job, 2.7 million. I'll flip to the next slide. So this is an example where there was a lot of pressure requirements in this space, and you can see that they had 14 different pressure control zones because we had a lithography area, we had the 5 production suites, which were along the left-hand side. They needed to do temperature control. They needed to do exhaust control because some of these were involved in viral vector type applications. They used a blade type volume control system. And while we didn't supply it in this case, our experience was it took quite a long time for them to get this balanced out properly. And it was a case where we started adding more air to some of the spaces because you'd get some pressure fluctuations when you get large, especially on windy days where you got, the buildings acting a little bit differently, or a stack effect depending on what's going on. And, the way to fix that, if you can't precisely control it, is to just simply create more offset between supply and exhaust. And so it did take quite a bit longer to tune this building in than had been our experience in the past. And, spending the time and sometimes maybe a bit more upfront cost on maybe a little better quality unit will definitely save you time in the long run. And I'm sure on these projects that time becomes a lot more important when manufacturers want to use this product at the end. Yeah, so David, I don't know if you have anything else to add, or do we want to open it up for questions?
No, I think we're good, Jeff. Thank you.